All right, doing this problem called search and rotated sorted array. This is in the list of that blind 75 must do problems. Essentially, in this problem, we are given a sorted array which has been rotated, and then we have to find out uh, the index of an element in the array. And I guess if the element is not present, then return -1. And we will do it in log of n complexity 4, 5, 6, 7, 0, 1, 2, and 4, 5, 6, 7, 0, 1, 2. Now, the thing is, basically we have to see can we apply binary search here or not. So let's see if we can apply binary search or not. So if an array is sorted, right, then how does it really look? So essentially, if your array is, let's say, 1, wait on 1, 2, 3, 4, 5, 6, something like that, essentially it's a increasing graph like that. And then when you do your binary search, you divide the array around the middle and you check the middle guy and the key that you're looking for, and you compare essentially. If the key that you're looking for is lesser than the middle guy, then obviously it has to be in this section, and if the key is greater, then obviously it has to be in this section. However, now if you rotate this array, right? So when you rotate this array, it can become something like 4, 5, 6, and then 1, 2, 3. That means what you will notice is, like in this case, the graph changes to something like it increases and then it decreases. Sorry about that, it's wrong. It's completely wrong. Uh, in this case, 4, 5, 6 is increasing. So let's make this the scale 0, 1, 2, 3, 4, 5, and 6. So 4, 5, 6 essentially is 0, 1, 2, 3, 4, 5, and 6. And then all of a sudden it drops. And then it goes 1 to 2 to 3. That's the that's how now our thing looks like. Let's take some more examples to see what are the different. So essentially, the slopes are always positive except a sharp downfall, right? So for example, another example would be a 5, 6, 1, 2, 3, 4. So here your 5 and 6 increases, all of a sudden you drop, and then 1, 2, 3, 4. That's the graph. So that's how the um, array changes to. Now within this array, within this, so let's take an example where let's shift things. Let's draw a line here. Say some things increase, 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 keep increasing, and then it drops, and then it drops, and then it goes here, right? Something like that. And obviously the middle is somewhere around here. So once you divide the array from the middle, what you will find is two kinds of subarrays. One of them will be completely sorted, and other of them will be having this zigzag, right? Like in this case, the left array is completely sorted, and the right array is a zigzag. I only need one part to be completely sorted to figure out the key that I'm searching for, in which whether it's present in this or not, right? So let's say this is let's say this is 0. So 1, 2, let's say this is 3, and let's say this is 8. Just for an example. And if I'm searching for 7, okay, so whatever. So 0, 1, 2, 3, 4, 5, it's called 6, let's 7, let's say this is 8. And now let's say I'm searching for 6. Okay, let's say I'm searching for 6, and so the middle value is 7 and 6. So on this I know that this array is sorted because this has 3 to 7, and this has 0 to 3 and 7 to 8. So basically, I check if what I'm looking for is if it's in my sorted section, which this is a sorted section, and it is in a sorted section, so I search within this, and then I continue that. So basically, whenever I divide the array, first I find the sorted section. So you divide around the middle, then find which part is sorted, and does the key belong in sorted section? If it does, then search in that. And if it does not, then search in the other section. Like this is one example where the left side was sorted. You can always think of another case where probably your right side will be sorted, right? So something like you have your um, increase till here, then it drops, and then it increases like that. And now if you divide around the middle, your right part is sorted. So you just figure out which part is sorted and check if the key belongs in that part. If not, then the key belongs to this part. Now again, this part, this condition will always be true. Now when you divide this further, um, again around the middle, again you will get, and let's say again if it goes into here, at some point you'll get here. One part will always be sorted, right? So that's the theory that we use and try and solve the problem. Okay, let's go to the code and see if we can convert this logic into code or not. So we are finding for a target in the array, and we have your left as 0, right as nums.length minus 1, and while left is less than or equal to r, only then we have to search, and outside of this obviously we will return minus 1. Or if you find, we'll return the index. Now while left is less than or equal to right, what you do is you find the mid. So mid equals to L plus or minus L by 2. And now obviously if your key is found, which is if your nums of mid happens to be target, then good, just return mid, nice. But otherwise, if that's not the case, then you find out if your left portion is sorted or not, right? So if my left portion is sorted or not, to find that out, I'll check whether the left is less than mid or not, right? So if first of all, if left is mid, so if left is mid, or Okay, so there is mid minus one as well. You want to check till, yeah, that's up to us, right? How you want to check. Let's check till mid. Makes it easier. So if this or uh, actually just mid minus one, yeah. So hmm. To make it simple, maybe just check with mid. So if nums of left is less than nums of mid, that means some left array is from left to mid, right? And the left array is sorted. But you want to check with mid minus one, no? I agree with that. What if there is a single element? If there is a single element, you don't have to worry about it because um, okay, let's not think about the corner cases and we'll adjust for the corner cases. The general idea that I want to check is if my left guy is less than or rather less than equals to, if they are duplicates. Are there duplicates or is this distinct? Nums are unique, okay? So fine. There's a nums of mid minus one. That means the left portion is a completely sorted thing. Uh, and then there is an else. So this is the case where left part is sorted, and this is the case where right part is sorted, right? So if left part is sorted, and if the nums of left, if the key is actually present in it, so if nums of left is less than uh, key, okay, it's just simple. So the key that you're looking for, the target, is greater than the nums of left, and the target is less than equals to nums of mid minus one. If target lies within them, then your right equals to mid minus one. Okay, somewhere you use left and right, somewhere you use L and R. Let's call it left, right, left, right, left, and right and left. Okay. So if then this, else you go left equals to mid plus one. And the other case is right part is sorted. In that case, you look into the right thing. So if the right part is sorted, then if your target is greater than nums of mid plus one and your target is less than nums of r, then your left equals to mid plus one. And if that's not the case, then your right equals to mid minus one. Now, I have not handled the edge cases, which is what I have to handle now, but that is the general idea. Now, what I mean by the edge cases is that there are only one element, there are only two elements, left and mid are equal, right? All of those things. So let's handle all of those nonsense. So one thing here is if left and right are equal, that means it's a single element, just return minus one, right? If it did not match, then just return minus one. So now you know there are at least two elements, right? And again, three elements is easy to solve. The reason three elements are easy to solve is because you'll always have a left, you'll always have a right, and you'll always have a mid. So everything is there. Like mid plus one is there, mid minus one is there. Now, maybe then solve two elements as well. So which is left uh, if right equals to mid plus 1, and handle that case as well. That case is simply, so in that case you have already checked mid, right? So then you just want to check basically in 0 and 1, what would you return as mid? 0 plus 1 by 2, so 0. So that means you have to check right. If right is equals to mid plus 1, that means, sorry, if right is equals to left plus 1, right? There's only two elements. Then you just do return uh, if target equals to nums of right, then you return right. Else you return minus 1. So one element is handled, two elements is handled, and three elements just will take care of, right? This is one element. I mean, this could also be one element. So basically, this takes, yeah, this is one element when you did not find a match with the mid. This is two elements when you did not find a match with the mid, and this is all other cases. Okay, run example test cases, and you got something cannot find symbol. Still, somewhere you're using or okay, run code. All right, run example test cases and submit. And you get a wrong answer. Why not? Let's debug it. So 2, 3, 4, 5, 6, 7, 8, 9, 1. And you are searching for 9, and 9 is present. Let's go to the whiteboard and see how to solve this. Where did the stylus go? Okay. So the question was, or the input is 2, 3, 4, 5, 6, 7, 8, 9, and then 1. So there are total 9 elements. You start with L equals to 0, R equals to so 0 to 1 to 9, so 8, right? And so this is 0. Let me write again. How about that? Okay, we write again. So I'll write the indexes first. So the indexes are 0, 1, 2, 3, 4, 5, 6, 7, 8. And the values there, values are 2, 3, 4, 5, 6, 7, 8, 9, and 1. And the target is 9. What? I don't need you. Okay, remain there. Let me just remove stuff. Okay, target is 9. Which we can clearly see is present. So now let's start our calculations. We'll start with L equals to 0, R equals to 8, and mid equals to 0 plus 8, 4 by 2. Sorry, 0 plus 8, 8 by 2, 4. Let me confirm with code as well. Yeah, left plus right minus left by 2. So 8 by 2 is 4. So mid is 4. So we get around here and we check, hey, 6, is it matching 9? No. Then we check, hey, is the left portion sorted? Like before that, we check whether it's a case of single or double. So left is right equals to right won't be true. Right equals to left plus 1 again won't be true. So we then comes to, hey, is my nums of left, just one sec. Yeah. So is my nums of left, which is 2, less than nums of mid minus 1, 5, which it is. So then I consider the left portion to be sorted. And then I see if my target is greater than 2, which it is, and if it is less than mid minus 1, 5, which is it is not, then I would look into this part, but I'm not. So I instead will look into this part. So now I change my L to mid plus 1, which will be 5, and R obviously remains 8. Then my mid becomes 5 plus 8 minus 5 is 3 by 2 is 1, so 6. So mid becomes a 6, which is this, right? Essentially, I have already discarded this. I'm only looking into this 4 now. And this is my mid. And now what I'm checking is, hey, is my left part sorted? And to compare that, I would check, okay. So this is probably where the problem is. The left can only have maybe a single element. And so, which is where I'm doing less. So the left part sorted, like I'm checking, check nums of left, which is 5, right? With nums of mid minus 1, which is also 5. And I'm checking if nums of left minus 1 is less than. I'm missing the equals to condition. So here I need to add an equals to condition. Okay. Now let's run just for this one and see if it works. If not, then we'll continue our walkthrough. So one, and it works. Let's submit again. All right. So a small miss, but good to debug. All right.